Okay, so as I was saying, the plan for the next few days is that today and Wednesday I'll finish talking about this duality stuff. I'll mention some more like mathematical properties in today's class, and then on Wednesday I'll give you this application to game theory, which is actually like a very nice application of the duality theorem. Um, and then Monday we will just kind of like do like this review type like office hours, if you like to call it that, like where I'll just like answer whatever questions you have. I already posted all the problems that I already updated the PDF with the problems for the exam. Um, so you should be able to do all of them after Wednesday's class. And it's like kind of like the usual where, like if you know how to do those problems, you'll be fine. Like, like I won't like this type of problems, I won't ask any specific problems that require the simplex method because we already covered that for the second exam and the final is cumulative. So like on the final, I'll ask you to solve things with the simplex method explicitly again. So this is more like these problems will be more like, as you will see on the PDF, of setting things up, like find the dual of the system of equations, or what does Farkas lemma would tell you. It's more like kind of like setting up the things, and then if you wanted to solve them, then yeah, you would maybe sometimes do the simplex method or something else, depending on what you're being asked to solve. But it definitely is less computational, and it's more like conceptual, like, and you do have to memorize like a bit more theory than for the second exam, but it's not that much more, like oh, sorry, let me cut this close. Okay, so today, yeah, what I'll say a few more things about duality. So basically, there are two formats about the duality that you have to remember. So version one, which is sometimes called like the symmetric version, and you'll see why, um, is that if you have a problem which is finding the max of c dot x, where the variables x are non-negative, and what ax is less or equal to b, right? If that's the original problem, the dual version of that is the mean of b dot y, where y is greater or equal to 0, and where c is less or equal to a transpose times y. Okay, so, and again, usually the original version is called the primal, which I'll refer to it as P sometimes, and the dual version is, it's just the dual, which I'll refer to as D. Um, so this was like the original version of how I wrote the duality, and it's called the symmetric version more because of what happens in the other version, which is what if you have an equality here. So in the symmetric version is with an inequality. Oh, maybe put this in color. So the symmetric version is like in the format less or equal to. Okay. The second version, which is like called the asymmetric one. Okay, version 2, which is the asymmetric version. Then the primal kind of looks the same, but now it reads ax equals b. So the main difference is that instead of being less or equal to b, it's just exactly equal to b. I'll just go check to make sure there's no one in the other room, although I did write it on the board, but I'll be back in 2 seconds. Okay, so for the duo here of this version, it essentially looks the same as what we had before, as what like the other duo is. The main difference is that now there's no constraints on whether the y's could be positive or negative. So the difference is that now y can be positive or negative. Okay. That happened because, again, if that's what we kind of did at some point, I think towards the end of the previous class. The thing is that you can think of an equality as two inequalities, ax equals b means that like, let me write it here. If you have ax equals b, that's the same as saying that ax is less or equal to b, and what, like negative b is less or equal to negative ax or something like that. So, uh, you get to or I mean, it's ax less or equal to b and b less or equal to ax. That's what I mean. But then you have to turn this into like a reverse inequality. And if you just play around with everything, like when you find the dual, you see that in the dual you always have like the difference of two variables, and so you just call that y, and it's kind of like what you end up getting here. But it's kind of like convenient to, it's convenient in to kind of like note both of them, but you see why it's called like asymmetric, because definitely there is more of a difference in this version. There is more of a difference between the x variables and the y variables, because now you drop the condition on y being non-negative. So in practice, it's more like for setting it up, because if you want to solve anything with the simplex method, it is useful to kind of like work with non-negative variables. So, you would have to re-express y as a difference of two variables, but it's got like a more concise way of writing it down, the the dual in this case. Okay. But in any case, like the strong duality theorem says that, that the max and the mean agree. Like, so like if the problems have finite solutions, then the I mean, there are other ways to write it, but like I'll write it like this. If the max and the mean are finite, then the value at the vector that maximizes the function in the primal agrees with the value of the function at the vector that minimizes it. So okay, does that make sense? Now, here's a cool thing, which is like the first fact that I was going to mention today, that there is a way to find the value where the mean occurs explicitly from knowledge of where the max occurs. So, so, so fact one there is a way find the value for where the minimizes the dual direct. There's a way to find this vector that minimizes the dual function directly from X max. Okay. And I'll give you like the explicit formula in a moment. By the way, I'll probably send you like a study guide for the exam tomorrow. I think I'll give you this formula because I don't think you would like, I mean, you could memorize it, but it's kind of those things like it's like a very specific formula, so I don't want anyone to lose points for not remembering perfectly, but I will kind of like write it on the exam without explaining what it says. So you have to just know what the meaning of the term, like the symbols are. And I think that's like a fair compromise. So I'll kind of like tell you, like write it down and I'll also put it on the board, but I won't say what what the symbols are. You just have to know what it meant. Okay, but so let me, before telling you how to find this formula, it's actually like a very fun exercise, and we will go through it because it's like a cool trick with linear algebra. I do have to kind of go back a little bit to this basis stuff that we had discussed for the first exam when we were, even before we learned the simplex method, we talked about like basic variables and non-basic variables. So it has been a while, so I'll just kind of like give you a quick refresher of what that was. But first, back to the basic variables, to the discussion of basic variables. So just to give you like an example. So if you remember, let's see. Okay. I'll just kind of, this is like an example we had worked on a long time ago from before. But it's kind of useful to think concretely with something like to have in mind. So if we had worked this example where we were trying to find the max of x1 plus x2, yeah, this was like maybe 5 or 6 weeks ago, I don't remember. So the conditions were that x1 was greater or equal to 0, x2 was greater or equal to 0, x3 was greater or equal to 0, x4 greater or equal to 0, and the constraints were x1 plus 2x2 plus x3 equals 4, and x1 plus x2 minus x4 equals 1. Well, actually, it was a bit before and not that long ago. Basically, this was like a problem where, these came from this like adding the slack variables as usual. This was one of these examples where we did like the auxiliary system first, because if you notice here, like there's this one with the -1, so like you had to add this even more extra variables, x5 and x6 in this problem, to get like the identity matrix, so that you could start the simplex method. But okay, long story short, right, like you do the simplex method here, this one would have required sometimes what's called phase one. But if you apply the simplex method, we found that the max, the vector where the max occurs was 4003. Okay. And so in this case, the basic variables, remember, like the basic variables are always the variables which, if the problem is non-degenerate, which is what you should assume unless you're told that it's degenerate, if the problem is not non-degenerate, the basic variables are always like the ones that are non-zero. So in this case, the basic variables are 4 and 3, right? But what was important about those is that was like the basic variables were always like associated to the columns of the matrix, if you remember. So if you if you recall, like what was the matrix A in this case? It's just like you know, the coefficients, right? So it's 1, 2, 1, 0, 1, 1, 0, -1. Okay, so what that means is that in this case, the basis, if you remember, what was the choice of basis? It was a choice of columns of the matrix where like you got like an invertible thing, right? So the basis in this case, like because I'm choosing columns 1 and 4, I mean I'm choosing the first and fourth entries of this vector, so it would have corresponded to columns 1 and 4, right? So the basis was 1 and 4. And I think this is like the notation I was using back in the day, first few classes. The basis would just be what you get by selecting those corresponding columns. So it would have been 1, 1, 0, -1, which is perfect because that one does have like determinant it's not 0, so it would have given you a basis, right? Is that like looks sounds familiar? Everyone hopefully remembers part of this. Okay, and what was that real? What was all of this for? Because if you remember, there was like if you called xb the vectors of like associated with the basic variable. So in this case, it would be 4 and 3, right? Then the cool thing that happened is that like and that's actually how we had found before we did the simplex method. That's how we would find the basic variables, right? The basic equation was that ab times xb would be the vector b, right? That was how, I kind of doing things backwards, but like what we did before is like you started with the basis for the matrix, right? You would solve this system, and that's how you would find the basic variables. So that was like the relation between the basic variables and the basis, right? And the vector b. Okay, is that making sense? Looks familiar, kind of hopefully. Okay, so now why is that useful? Um, okay, let's see. Notice, like in particular, because of, um, you know, let me put this like a bit more explicitly, because like the matrix A is invertible. Another way to think about this is that you can say that XB is AB inverse times a vector B. That was another, like, that would be convenient in a moment. Sorry, just to go back for a second. Yeah, like I like like I just remember like that I miswrote this because the point is that at the max or the mean, like like the values are like you don't have to maximize or minimize anymore. Like the point of the duality theorem is that the values of these two functions agree at the max and at the mean. So there was no need to put max or mean, like that was unnecessary. Just to before like going give you like this formula. If you look at this example, like the function was the max of x1 plus x2, right? So if you write it in the notation that I'm using here, where the vector is like x1, x2, x3, x4, right? Then the coefficients are 1, 1, 0, 0. And because we're focused in columns in the first and fourth entries, right? Because our basis, again, our basis is associated with entries 1 and 4. So it's not like a notation that was used necessary before, but if you extract the first and fourth column, the first and fourth entries here, you could also kind of like refer to the coefficients associated to that basis and that would just be the vector 1, 0 in this case. So this, like again, like whenever you put the B for basis, that just refers to like the entry selected by the basis and or the columns. That making sense? Okay, so why is all of this useful? So now I'll give you, as I was saying, my goal is that if you have, this is cool. Again, if you know where the max occurs, if you know the vector that maximizes this function, you can immediately find a formula for the vector that minimizes the function in the dual. So that's kind of like nice to know. For a purpose that will be useful in a moment, which is this relation of these two variables to what I had said are like the Lagrange multipliers. Even if you haven't taken multivariable, you don't have to worry because I won't say anything about multivariable, but like you do need, like, this is where it comes from, what I'm about to say. So, um, so back to the duality theorem, right? So again, like the duality theorem says that the value at the max of the first function equals the value at the mean of the second function. Okay. Now, if you remember how a dot product works, right? Like a dot product is just a bunch of products added together, right? So when you're like, I'll kind of like write this down in two different ways, but what is the first quantity, right? It's like C1x1 plus C2x2 plus C3x3, right? Until the number of variables, whatever that number is, right? That is what a dot product in general is. But in this dot product, the only thing that can survive in these summands, like the things that you're adding, only when the variable is not zero, you can get like, a non-zero answer. If like the variable happens to be zero, like then this doesn't contribute to the dot product, right? So only when like at the basic variables is this product relevant, if that makes sense, right? Because if x is like a non-basic variable, like then its value is zero. So like you don't care about it. So in this dot product, really the only thing that contributes to it is the values the non-basic variables, right? Only the basic variables contribute to the dot product. Is that making sense? Because again, if a variable is non-basic, that means that its value is zero. And if its value is zero, that means like it could be this factor, right? This term, and then this one is zero, and zero times anything, it doesn't matter what it is. So what that means is that you only have, so in this dot product, what I'm trying to say is that you only really have to remember about the dot product between the basic vector and the coefficients of the corresponding to the basic variable. So you can kind of like replace this um, with this. Okay, so far so good. Okay, now here comes the cool part, which is like the linear algebra. First, I already just gave you like 2 minutes ago, like a formula for the basic vector, right? The basic vector, what is the basic vector? It is the inverse of this basic matrix times the vector v. So I'll replace this. So again, this is AV inverse times the vector v. Okay, is that okay? Is that making sense so far so good? Now, why is that interesting? Because if we were just working everything with ordinary numbers, if everything was were numbers, no vectors, then you would cancel the b's, right? Because they appear on both sides of the equation, and that would give you an equation for y mean. So you really should think that I'm about to do kind of like the next best thing to that, but kind of like the idea is that by rewriting in this way, b is on both sides of the equation, so you would like to cancel it. It's just that you have to be a little bit more careful here because with dot products, you cannot just like cancel dot products, but you can kind of like do something close to that, and that will work, you'll see. So the first thing is that, to look at, I do want kind of like the factor b on its own. Here, it's totally fine. It's already alone, but here b is being multiplied by the inverse, which is kind of like annoying. But I had mentioned that this is kind of like the magic of the transpose. The transpose has this magical property that you can move the matrix to the other factor if you are willing to take a transpose. So um, this becomes a V inverse transpose CV dot V equals V dot Y main. Is that making sense? And like again, I'm trying to find a vector like that would make this equation work. And it doesn't matter in which order like you take the dot product, so you can put like kind of you can rewrite it so that the factors like so that v appears on the first factor on the left, like appears on the first factor on both sides of the equation, right? So again, here I'm trying to find where the y mean could happen, right? So the easiest thing you could do, like to make this equation work, is just like, you just want to take y mean to be this. And it actually ends up working. Like that's the, you can kind of check that that's like a basic feasible solution for the dual or whatever. But at least I'm trying to tell you where the formula would come from. So you just kind of like choose a vector that makes like this equation kind of like automatically be true. And then you do have to prove that it happens to work. But like, uh, and that's it. This is like the formula I'll give you on the exam because it's kind of like not too bad to memorize, but also like I don't care too much like giving it away. But I won't kind of like tell you the meaning of like the formula. So you do have to remember what it meant. So you can take, so one can show, like I will say it like that. One can show that y mean equals AV inverse transpose times CV. I'll show you how it looks like in the problem we were just solving. So yeah, I'll give you this one on the exam. I'll provide it. I will give this one on the exam. Okay. Um, and I'll show you in a moment why that's a useful formula. It's like a kind of like it's what is useful for what's called sensitivity analysis, which I'll explain in a second what that means. Um, but like just to go back to our example, we had the vector CB, right? What was CB? CB was 1, 0. and AB, what was AB? AB, I had also written it here. AB was 1, 1, 0, -1. So you can find, and also I would give you the formula for the inverse of a 2 by 2 matrix. I also don't care about that. So like I would give you the formula. So, but then if you do AB inverse transpose, like you kind of like, like it's not like a long, like a 2 by 2 matrix. It's not too hard to find the inverse anyways, like from scratch. But, as I was saying, like I would provide it. So it's not a problem. Um, and so that gives you 1, 1, 0, -1. And so what that means is that this vector y, so the vector that minimizes the dual is AV inverse transpose times CV. And so that would be 1, 1, 0, -1 times 1, 0. And that would give 1, 0. So this is the vector that gives you the solution to the dual problem immediately. Which, by the way, is like a useful exercise to convince yourself, like you should try it. I mean, with the recipe that I wrote at the beginning of the class. So just to go back for a second, I gave you like a formula. How do you find the dual from like the equality version of the optimization problem? So you can check. It's just like taking you just need to take the transpose and other things, but you should check that the dual. I'll leave it as an exercise, but it's like a useful exercise to do. Check that the dual problem was the mean of 4y1 plus y2, where so these conditions these are the conditions that this is what you get if you write what that C is less or equal to A transpose Y. This is equivalent to it. So there are no extra conditions. Like again, in the dual, in this version, like you don't have to ask for the variables to be non-negative. In this case, for example, like y2 will be negative because negative y is positive. So this one kind of like works like without that requirement on the positivity of the variables. And like, it is this is like a tedious like problem I mean, you could solve it with the simplex method. Like, if I had given you the simplex method to solve this, but then you have to turn it first into a max. You have to, add slack variables and also reverse the inequality. There's so many things that you would have to fix so that it kind of like goes back to the format that we had for the simplex method because our simplex methods were always maxes. I mean, there's a bunch of things that you would need to do. So like, it is kind of nice to know that you can kind of like just immediately tells you what the dual is. Because again, and if we had time like to talk about like there's a bunch of economics applications to all this stuff, but the way to think about the dual is that the dual is what appears when you are trying to play with the inequalities. Like if you had like the max problem and you were trying to find how do I play with the inequalities to kind of like constrain the max, then those coefficients that the dual gives you is like by what amount you have to multiply the numbers in each inequality. So the thing is like those numbers like in economics have some interpretations in terms of like I think they're marginal cost or something like that they're called. So like I mean that knowing understanding the dual problem is like a useful thing on its own right. Like it's an interesting like thing like, to know about. I don't know. Maybe the book does mention a little bit of it, um, but definitely it does have like a lot of like useful interpretations. I'll kind of give you one of it in a moment now that we have some stuff in place, and you will next time we'll talk about this max min game theory stuff, and it like the dual there like it will be kind of like a fun thing because it's well, I mean, maybe you are too young for this, but this was back in the day. There was this game, rock paper scissors. I don't know if you've heard about it. Um, but you know, like there's a bunch of games like which are called zero sum games, which I'll tell you next time, where like you could imagine playing so rock, paper, scissors, like the way it worked is like you know, how is it? You have rocks that beats scissors, and then scissors beats paper, which makes sense, right? And then paper beats rock because like you kind of wrap around the rock, and somehow that defeats it for whatever reason. So you have like this game where like everyone choose like one, you have to choose kind of like you know rock, paper, scissors, and you know like that determines which one wins, like what I just told you. And then you could imagine making bets on that game, like you know, the winner on each round gains $1, right? So it is a zero sum game because if you lose, if someone wins, the other person loses, right? Like it's not possible the way it's designed for both to simultaneously win. So your gain equals my losses on a particular round. That's what makes it like a zero sum game. So you could ask whether there's like an optimal strategy that in the long run, if you had to play against someone like a million times, you know, that um, kind of like you wouldn't kind of lose, you would lose the least amount of money or you would gain as much as possible. Like, you know, if you don't know what the strategy of the other person will do. And kind of like there's this theorem called a Nash, it's kind of like a Nash equilibrium. But there's like a theorem of von Neumann that like there's like an optimal strategy, and to show that there's an optimal strategy, you can use like the duality theorem from here. So I'll kind of tell you how all of that works because it's like an interesting thing, and game theory has a lot of like applications, you know. Um, in economics and other places, like even politics, you know, you probably have heard about this prisoner's dilemma and all this other stuff. So, you know, it's kind of like a baby version of all these things. So it's kind of like, and they're like both the dual and the original problem make a lot of sense. And so it's kind of like nice to see it in a concrete example. Because the way I introduce everything, it's kind of like the original problem is being prioritized. But the dual is kind of like in its own right, like an interesting problem. So like once we talk about this game theory stuff, like you'll see, okay, they kind of like are both like interesting things to know about. But I'll tell you a lot. Like it doesn't take too much time, but it's kind of better to have like a fresh mind there. But yeah, like you know, like it's kind of like there's a lot of mathematical theory about gambling also. Like, you know, like you probably have seen these movies about how to like these mathematicians from MIT, I don't remember like what was like the university that had gone to Vegas and made hundreds of thousands of dollars. Well, that was years ago, but like because they like there are ways to count cards like using like statistics and probability theory. So all this stuff, like, you know, um when there's probability involved, like they're like interesting applications. And like in this game theory stuff from next time, you'll see where like the probability appears because you want to on average win. So there's some expected values that you have to find. Like and but I'll tell you about that next time. So okay, so I did want to give an application of this formula, but before that, are there any questions or so good? Okay. So this is like an interesting application of the formula that I just showed you. So, which is called sensitivity analysis. Application. And like this course is kind of because I do check the Rutgers Reddit, I do find it very fun. But like, if you look at comments for linear optimization, people always complain about it. But it is kind of like one of the really important courses. Like if you want to use anything in your career, like, like if you most jobs, like if they involve like anything strong on computer science, like, they will ask you whether you know linear optimization or not, because like almost everything is still like you linearize first. Like that's kind of like the philosophy of life, like linear stuff can be solved. So even if a problem is very complicated, you always try to solve the linear version of it first. So like linear optimization does have like a lot of like interesting like avenues, like you can take it, like machine learning, neural networks, or like, these like applications to economics. So it's kind of, like it does seem very kind of like simple in some ways, because it's just like reducing those matrices and all that stuff. But like, it kind of like many things just fit into that paradigm. So um so definitely, like I feel like I'm to the extent that's possible, it's good to kind of like at least give some sense of where are all the possibilities where you could use this. But if you read the book does have like many good examples, like for networks and other stuff, like which maybe depending on how much time we have left, we can cover some other things like that. But I do think this game one that we'll do on Wednesday will be a useful one. So okay, but I have said a bit too much. So what is this sensitivity analysis? So okay, I'll give some names just to make it more clear. But imagine that you have the original problem where I'll call this the typical optimization problem we have been working with. So, in sensitivity analysis, sensitivity, like, imagine like you have to, like, again, it's kind of like in practice. So in practice, what can these numbers refer to? They could refer to the prices of like manufacturing some good, like it could be the cost of like, certain items, like, like the aluminum, copper, whatever goes into the production of like something, right? Or it could be like the measurement of like the height in statistics, right? Like you're measuring a population and then you're measuring their heights or their ages or their weights, and something like height or weight or like, even like the amount of a product in dollars, like that is not like a fixed number, right? Like that will fluctuate either because if it's a measurement, because there's uncertainty in measurements, right? Or if it's like, like if it's like costs, like, things are volatile, like, kind of like stocks and all of that can fluctuate a lot. So in practice, like you don't want, when you solve a problem, it would be kind of suck if you could only solve it with those exact numbers. You want to kind of like give yourself some wiggle room and ask, well, if I didn't have if the numbers had been varied by a slightly small amount, how much would my answer have changed, right? Like, that's kind of like a natural thing to ask. So what I'm going to think in kind of like the easiest thing that you could do in this case, like the numbers could change in many different places. They could change because like these coefficients change, or because maybe the entries of the matrix change. I would change just like the most basic thing here, which would be the constant terms that appears in the inequalities. Like there are other things you could change, but that's like a little bit harder to understand. So like here, like imagine that you change the vector b a little bit, that you change a tiny amount. Okay, and I kind of will use a physics notation. So every tiny amount that you change is a delta, right? Like delta is always represents like a small change. So I'll call this v nu, which is kind of going to be my original vector of constants plus a small change, right? So this is kind of like, imagine that this is like a very small change in the vector. So it's like a small change. So like what you should think about it is like the entries are relatively close to zero. Like the individual entries of this vector are small numbers. Like, each entry of this vector is really small. It's kind of like when we did the perturbation analysis, if you remember that we had like this epsilon 1, epsilon 2, epsilon 3. It's kind of like a similar idea. So it's just like a tiny amount you move the constants. So the question is, now you have the optimization problem, which is exactly the same as the one before, but the vector of constants was changed by this extra amount. So the new problem, I'll call it new of or perturbed. That's how you could also think about it. Like, but I'll just keep using the word new. So the new optimization problem is going to be the max, right? You're having the same stuff as before, but now you're using B plus delta B. So the only thing is that now, again, I'm solving the problem in the with a slight change of constants. Yeah. And also, like, actually, let me write it as an, not that it matters too much, but you can turn these into equalities if you add slack variables. So like, actually, I'll think about it that way already, because that way I can just use that formula that I wrote before. So. So if you see, like, again, I kind of did the minimal amount of change where I kept the coefficients of the function the same. I kept the entries of the matrix the same. The only thing I changed was like the constants that would appear on each equation, like I just changed those a little bit. Is that okay? So the question would be is like how, each of imagine each of the problems has a max. Like, we're in the bounded case, so there's not like infinite solution for the max. So if there's a max for the first problem and there's a max for the second problem, how much do the functions differ? How much do the values at those maxes differ? So the question is like if, you know, so here let me write that question like this. If let's call that alt. If this vector saw maximizes the original problem, and let's call it new for the other one, and x new maximizes the new problem, which is perturbed. Like that's how you should think about it again. The new problem. How much do the optimization functions change? How different? How what is the difference? Because again, like this is the value of the function at the max. This is the value of the function at the max. So kind of like, again, if just to go back to this economic example, you could think about the optimization function could be your profit, right? Like, so the constraints are telling you you are trying to maximize your profit subject to certain constraints, right? So the max is what is the maximum amount of money you can make, right? So what this question is like imagine that now you're given different constraints, because maybe again the prices for the goods that you have to purchase for producing your product changed a little bit. So your profit margin will change. So what this is asking is how much does like the new profit can be compared to the old profit, if those changes are really small, like if there's not a big change. Um, the reason why you have to think of the vector as being small is that if you make a large perturbation, you can kind of like get sucked into the degenerate case, and then kind of like that messes things up a little bit. because then, in the degenerate case, certain formulas, don't work quite as well. The idea is that if the perturbation is small, if the max happens, like the basic variables essentially do not change because like the change was so small that the max, it's kind of like, similar to like what would happen, like if you think about it with a triangle. If you have like a triangle, oops, like, okay, if you have a triangle and let's say that the max happens at the top corner, if you move the triangle a little bit, like the max cannot jump to one of the lower corners because it's a continuous function and the max has to be at a vertex. So it cannot go possibly from the top vertex to the one of the lower vertices. That would be like a drastic change. So by continuity, it cannot occur if like the change is really, really small. So essentially, like just to kind of like write it more explicitly, the idea is that if the perturbation is small, if delta B is a small vector, um, the basic variables, for both vectors are the same. Not in the sense that their entries are the same, but rather like that if it's like the first and the fourth entry in the first problem, it has to be the first and fourth entries in the second problem as well. So meaning that you can use the same basis. That's what I'm trying to say. So the basis for old problem is the same as the basis for the new problem. Okay. And now here comes the cool thing, because what is this difference? Okay, by the duality theorem, each of these is the same as the value of the dual function, right? So let's try to work this out. Okay, so I'll write it like this. First, I'll write it as delta max. So by that I just mean like this, we're trying to find the change in the maximum value, like the maximum profit. That's how you should think about it. And then I'll tell you how this is. After we do this, I'll tell you what the relation with the calculus is. But okay, so delta max is just how much your maximum profit changes, for example. Um, so originally it would have been this, but because of duality, you can replace each of these dot products with their dual versions. That's why how duality is supposed to go. So duality theorem tells you that C times X nu would be the dual values. So V dot Y nu, and then the other one is B dot um oh, sorry. Like that's the thing. Like the that's the cool part. Like, so I have to be a bit more careful. Like, let me call it V new. Like, V new dot Y new minus V old dot Y old. Where, like, by this I just mean that you look at the dual for each individual problem, and there's like a minimum solution, let's say, and then I'm calling them Y old or Y new, depending on which one you're looking at. Okay. But what is the V new? V new is like the old vector V plus this perturbation term. So it just gives you this. That is what V new is. Now, what is Y new? That's why it's important to have this formula. I mentioned that we have this formula for how to find the vector where the mean occurs in terms of the basis. That's the cool thing. So I will replace I'll replace the new vector with it. And that's the nice thing, like this, like we didn't perturb the coefficients of the functions. So I don't have to specify whether this is new or old, because the only thing that the only thing I perturbed was B, not like anything else in the matrix. So that's why I don't have to say whether this is new or old, because it's kind of like constant. And then this is B old, but what is B old? That was just B times Y old, but Y old is actually, that's a cool thing. It's exactly the same formula, because in this formula, nothing depends on the vector of constants. They just depend on the matrix, and it also depends only on the coefficients of the function. Sorry, let me put, just to make this clear, this is a minus sign, and this is a dot product. Okay, perfect. So the cool thing here is that because of this specific perturbation, these two vectors are the same. Nothing changed here, which is kind of crazy. And so you can factor it. So, and so what do you get? You get delta, like the b's cancel, right? And so you get delta b dot. And what is this thing? I mean, now that we know that it's the same, I can just call it y mean, because it's the same vector that minimizes both problems. That's like the interesting thing. That this one work, like I'll kind of write it explicitly, because it's kind of like important to notice that this vector works both for the original problem and the new problem. So it's the same vector for old and new. Okay. So what you end up with is that the change in the maximum value, by like how much your max changes, is a dot product between the change in the perturbation that you made and the vector that minimizes the two. And okay, this one is another of the formulas I do expect you to know. I mean, I don't think probably, well, maybe I'll provide it. But yeah, again, like I will not put like the meaning of this, but like it's fine. Like, it's okay to just give it out. I'll give it, but like you just have to connect the dots, to what we were saying before. But what this says is like, again, if you think about it in terms of profit, you have the profit, you change the value of certain input prices that you have to use in manufacturing your product. That changes by how much your profit could go, like your profit could go up or down, you don't know. And so what this tells you is like, how much is the maximum profit that you could make? How much does the maximum profit that you could make changes? Like, um, okay, and so what's the interesting interpretation of this? So I'll kind of like do it kind of like in Calc 1 interpretation, so that there's no assumption of multivariable calculus here. So let's just pretend that everything is just scalars and not vectors. Like, I mean, this is, oh, sorry. I mean, what I mean is that this is a vector, this is a vector, right? The max is just like a number, because it's like a function, right? Like just a scalar. So this is like a scalar, but this is like a dot product, which is why you also get a scalar, right? But let's just pretend that everything had like one entry, so that there's no dot product. So like, just pretend the vectors have only one entry. So what do you get? You would get that the delta max, the change in the max, is delta B times y mean, right? Like no more dots needed and no more arrows needed. So what do you do next? You divide by delta b, right? So you get delta max over delta b equals y mean. Does the left hand side look familiar to something like that notation? What does that remind you? What does that look like if you take delta b going to 0? If you thought about a limit as delta b goes to 0. It's one of the two main things in calculus you can find. Oh, oh well, the thing is also the change in max also shrinks, right? It's it's kind of like a 0 over 0, right? But but it's like a derivative because if you look at the derivative, right? What was like a derivative? Like a derivative is kind of like the limit as h goes to 0 of f of x plus h, right? Minus f of x over h. If you call instead of h, call it delta b, right? And then this is like a difference, so it's also like a delta. So the derivative is like a rate of change, you know? So this is kind of like a rate of change. So what that says is that the y mean kind of you should like the way you would write it is kind of like the derivative of the max with respect to b. Roughly, that is like y mean. So the variable that minimizes the if this were literally calc 1, right, like, where you're just dealing with variables and not vectors, then the variable that minimizes the dual is a rate of change, is a derivative. And there's a generalization of that, which is roughly what the Lagrange multiplier is. That is like if you have taken multivariable, because in the Lagrange multiplier, like so yeah, sorry to so, but this is kind of like you should think about it in that way, and it's like a useful interpretation. So roughly, like the variables that minimize in the dual problem are kind of like rates of change. That's okay, an okay way to think about it. So the variables that minimize the dual are derivatives in a sense. So that is like an interesting interpretation of the dual variables, which is not obvious from the beginning of the problem, you know. And if you have taken multivariable, I'll just bring it up for those who have taken multivariable, like you have like these Lagrange problems where it's like kind of like the gradient of the function equals lambda times the gradient of g, right? Again, if you pretended that everything is one variable, like what is a gradient? It would have if this were literally just one variable, it would be the derivative of f with respect to x, because there are no entries, right? Like, and then lambda times the derivative of g with respect to x. And then like if you cancel the dx's, right, you get the derivative of f with respect to the derivative of g would be lambda. This is essentially the same structure as this, it has like the same format as this one. If you just think of f as max, as the maximum function, and g as a constraint, which is like the constraints, like, that get when you equate to b. So that's why really like the Lagrange multiplier is kind of like the dual variable. So, and that's actually true. Like, if there are ways to set this up so that like this is like a Lagrange multiplier problem, what we're doing, but just like a very specific one because everything is linear. So I could have called the dual variables lambdas from the beginning, and that connects it more clearly with multivariable for those who have taken it. But it's kind of like nice to not start there, and then you kind of realize, oh my God, this is actually the same thing we were doing before, but in a very secret way. So the Lagrange multiplier is kind of like the dual variable. Again, for those who have seen it, if you haven't seen this, no worries at all, but it's still worth mentioning, I feel, because it does kind of usually if you ever take multivariable, you're solving these Lagrange multiplier problems, and sometimes it's not even clear what the meaning of the Lagrange multiplier is, but it's literally at what rate of change does the maximum change as you change the values of the constraints, like of the constraint function. again, you have to be a bit more careful because strictly speaking, there are more variables involved, but you can kind of like do something that kind of like gives you the same interpretation. But it's still, uh, it's still a good thing. But yeah, I mean, I suppose like like if you look at the PDF, you'll see how I asked this question. There's not much to ask about it. It's kind of like a useful thing to just discuss so that you interpret what's going on in the class. But yeah, I don't think there would be too many direct questions that I would ask about this one. Of this one, yeah, I'm more interested in asking this because it's actually computational. So you have compute things, but I would kind of like tell you, okay, this problem had the max here, so you had to identify the basis. Once you identify the basis, then you can do the multiplication and do. And as I was saying, I'm not expecting you to solve anything with the simplex method for this exam. So I would just kind of like say like what the answer was supposed to be, kind of like as in here where I tell you, oh, the max happen to be this one. So I want you to identify from there like the basic variables. You construct the matrix AB just like as before. You construct the coefficients and all of that stuff. Uh, but I would kind of give like the answer for where the max occurs because I'm not interested in you solving the like just the problems with the simplex method. Until the final, we will use that again. But and yeah, and this thing is kind of like a cute like observation. So like I felt it was worth it. So next Wednesday, as I was saying, we will do this game theory stuff, which would be the last topic for the exam. And I'll try to send you tomorrow maybe like a summary of like the study guide and all that stuff. But yeah, let's end here. I think that's a good place. Yeah. Mm-hmm.
Scroll up a bit.
Yes.
A little more, yeah.
Yes.
So for the new Y, right, the binomial row,
Right.
A inverse CB, right?
Right.
And then, like, when you make the formula, you had the A inverse of trans.
Oh yeah, actually, now that you say, no. So, oh my God, so sorry. Thank you so much. You just saved us. Yeah. Like, how did I forget this part? Yeah, like there was a transpose here. I just forgot to copy it with transpose. Excellent. Yeah, it doesn't affect. I mean, everything that I said is okay, but yeah, like there should have been transposes everywhere. No, good. I'm so glad that you caught that. Thank you. I think now we're good. Yeah. Yeah, perfect. Woo. Anyone else? Okay, cool. This is a good place to end. And yeah, so next Wednesday we'll talk, not next Wednesday, this Wednesday we'll talk about this game theory stuff. So let's change here.